Exercise 6b, proof by contrapositive. So today we're learning about proving statements using the contrapositive statement. What you need to be able to do is negate statements and prove their falsity, write the contrapositive statement, and prove its truthfulness. This might sound like a little bit of jumble in terms of that success criteria, but what we're really doing today, those are the sort of broken down bits to it. We're just learning a different way of being able to prove certain types of statements, and those are the things that you need to be able to do in order to prove by contrapositive. Now, why do we need different ways to be able to prove statements? We've already learnt direct proofs, but that only works for certain types of statements. So if you take this example, if n squared is even, then n is even. Let's try to apply our direct proof technique to this. So usually what we would have said is let n squared equal to 2a, because that's if n squared is even. And then we would figure out what is n. So n, we would take the square root of it, and we get the square root of 2a. Now, logically, we know that the square root of an even number should always be even, and the square root of an odd number should always be odd. But if we were to write that in a proof, then you would actually need to go ahead and prove that statement itself, because this doesn't look like the traditional way that an even number does. Remember, we always want to get to the point where we've got an even, which is 2k, or an odd, which is 2k plus 1. The square root of 2a does not really suit either of those styles. So sometimes statements are not really easy to prove when we are using the direct proof method, and so we need to look to different proofs or different methods that we can use to prove statements. So the method we're going to look at in this exercise is called the contrapositive method. So they're really good, direct proofs are really good at proving simple statements that have an obvious conclusion. But there are some that are really difficult to prove as they are phrased. So what our job is to kind of change the way that they're phrased and be able to prove the way that that statement looks. So we're going to change it using and create a contrapositive statement. Now, there are two sort of things that you need to do in order to create a contrapositive statement. The first thing is to negate the hypothesis and the conclusion, and you also need to change them around. So there's two stages and two things that you need to do. We're going to practice both of these individually. So first we'll just look at what does negating a statement do, and then we'll have a look at building the contrapositive statement by interchanging the hypothesis and the conclusion. So for now, let's just focus on negation. Essentially, negation is just to do the opposite. So not. If I were to negate a statement P, it suddenly becomes not P. And if you want to use mathematical notation, we can also write it using this symbol, so not P. Here are some examples. The sky is green. That's false. The sky is not green. That's true. 1 plus 1 is equal to 2. True. 1 plus 1 is not equal to 2. False. So you can see here that the opposite statements where we insert a not or the opposite gives me the opposite effect. So one is false, one is true, and so on. There's different ways to be able to negate as well. So all prime numbers are odd. So instead of saying all prime numbers are not odd, we can also say there exists an even prime number. This is also an opposite statement. So if we're making a generalized statement about everything, we can say that no, instead of it being everything is odd, there is some sort of number that exists that is going to be prime. And we're going to have a look at these statements in a different exercise. So there's also all triangles have 3 sides. We can say some triangle does not have 3 sides. So there's different language to being able to negate. Today we're really just focusing on this type of language here, but those two other statements are also negated statements from the original. The key thing to take away here is that negation turns a true statement into a false and a false statement into a true. So we're going to go ahead and practice negating some statements. So first of all, we've got write down each statement and its negation, which is true, which is false. 2 greater than 1. Hopefully we can all recognize that that is, whoops, can't believe I just wrote false. That was true. My mind's just going ahead to the next part, which is negating it. So what's the opposite of 2 greater than 1? It is 2 less than or equal to 1. Notice I put the equal as well because I want to make sure I've covered all grounds. So here it's not talking about equal, therefore the equal must belong in that second statement. That is now false. Okay, next one. We've got 5 is divisible by 3. That is false. What's the opposite of 5 divisible by 3? This one, it's simple. 5 is not divisible by 3. So I've just written out the original statement, but I've included a negation to it as well. This is now true. Okay, next one. The sum of any two numbers is even. this time, we can say the sum of any two numbers is not even, but because in maths there's only two options, you're either even or odd, we can actually change this to say the sum of any two odd numbers is, either you can say not even, or you can just go ahead and say odd, because that's the opposite of it. Now, the sum of any two numbers is even, that would be true, and this one would be false. Finally, we have there are two prime numbers whose product is 12. This one's a little bit more tricky because of the placement of our not. So instead of saying there are two primes whose product is not 12, that doesn't, I mean, it makes maybe grammatical sense, but it doesn't make mathematical sense, because we're not really talking about the product being 12. We're talking about, are there two numbers who when multiplied together gives me 12? So the reason that this is false is not because about the prime numbers not equaling 12, but rather, are there two numbers that equal 12? No, there aren't. So then the negation of it would be there are no two primes whose product is 12. So the subject here is about the primes, how many primes there are, like what primes equal 12. The equal 12 is kind of just the conclusion part, whose product is 12. So this is the part that we need to negate. And I guess that's where it gets tricky. How do you know what to negate? And I suppose it's just thinking about the overall purpose of this statement. So this statement is about the primes, not necessarily about the product of 12. So that's why we negate that section there. Okay, so these are all pretty straightforward, aside maybe from that last one, but we are going to get into something that is a little bit more complicated, and that is when we are negating two items or more, but we're just going to be focusing on two. A really quick way to understand how we can negate these is to look at Venn diagrams. So if I quickly draw up two Venn diagrams, oops, didn't mean to do that, like this, and say this is Venn diagram A and this is Venn diagram B. So if I have A and B, so the intersection of them, if I want to then consider what is the negation of that, so what is the opposite to it? Now what I can see is the opposite to A and B, so not that would be everything except for that part of the red. Now what is that also? What is another way to write it? You might remember this from set notation when we did that topic. So this is actually the same as saying not A or not B. How does that work? So what is not A? I'm just going to use a highlighter. Not A is everything on the outside, but also everything that belongs to B that does not also belong to A. That is not A. What's not B? Not B is the same idea. Everything that belongs to A that doesn't belong to B, and also the outside. So you can see that that blue shaded area is the same as the pink. So these two statements here are equivalent. So where does that take us in terms of being able to negate things? When I have more than two items that I'm negating, so if I'm saying not P and Q, that's the same as saying not P or not Q. Same idea as this. So that's not A or not B. So the and changes to the or. Now it actually follows the same if you try the other way. So not P or Q is the same as saying not P and not Q. So you negate each of the items individually and the and changes to an or that or changes to the and. And this is called De Morgan's law, and it explains how to negate statements that uses and or. Let's go ahead and practice this concept. So write down each statement and its negation, which of them is going to be true and which of them is false. So let's look at this first one here. 6 is divisible by 2 and 3. We know this is true. Both 2 and 3 go into 6. So if we were to negate it, we essentially want to create a false statement. We know that we need to negate each individual part. So we would say 6 is not divisible by 2, or 6 is not divisible by 3. So now when we have a look at this statement, this is false, this is false. So overall, this whole statement is false, which is what I expect when I negate a statement that is true. Now this is for part A. If I look at part B, 10 is divisible by 2 or by 10 or by 7. This statement is true. And the reason for that is that 10 is divisible by 2. It's not divisible by 7, but I've just got an or, so it has to be divisible by only one of them. So what would be the opposite if I negate it? It would sound like 10 is not divisible. Oops, divisible. by 2 and 10 is not divisible by 7. So this section, 10 is not divisible by 7, is true, but this part is false. And because it's an and statement, and means I need both of these to be true, both of these premises. And in this case, they're not both true. So this overall is going to be false. So you can see how when I negate something that has an and statement, I need to consider both of them separately, and I change the or to the and vice versa. All right, we're finally going to apply it to our favorite scenario, which is about Alice and Bob, their residents on an island where there's knights and knaves. So this time, Alice is going to say, I am a knave, or Bob is a knight. We're going to split it up into cases as we did last time. So suppose that Alice is a knave. So if Alice is a knave, then Alice is not telling the truth, which means the statement that she says needs to be negated. So let's go ahead and negate this, and we know that when we have an or, we need to change it to an and. So that means Alice is a knight, and, so not A and not B, and Bob is a knave. Now here's our issue. This is working on the premise that Alice is a knave, but now we've come to the conclusion that Alice needs to be a knight if I negate this statement. Therefore, this statement can't be true because Alice would be both a knight and a knave. That's impossible. Can't be both. So let's move on to the second scenario where Alice is a knight. If Alice is a knight, then Alice is telling the truth. If she's telling the truth, then the statement stays as it is. So Alice is a knight. Alice is a knave, or Bob is a knight. Now remember, for an or statement to be true, only one of the premises need to be true. So in this case, we've said Alice is a knight, and then her statement is that it's a knave, that she is a knave. So that part can't be true. Could she be telling the truth about Bob being a knight? Well, that is the only option left, because if she's a knight, she's telling the truth. She told us she's a knave, which is clearly not true. So only the second part must be true in order for her to be a knight. So Bob must be a knight. That's the only way for her to be telling the truth. So if Bob is a knight and this premise works, then Alice must also be a knight. So therefore we conclude that Alice is a knight and Bob is a knight. Oops. Oh, Bob is a knight. Okay, so that is the first half of this exercise, which is about negating. So where are we going with all this? In order to create the contrapositive statement, which is a statement that we've switched around to help us prove it a little bit easier, what we do is we negate both of the conclusions in the hypotheses, and we also switch them around. So you negate them and you switch them, and you'll notice that the statement remains true, or if it was initially false, it'll remain false. So here's an example. If it is the end of the term, then the students are happy. So here is the negation and the switch. If the students are not happy, then it is not the end of the term. So that makes sense, right? This is one side of it, it's the half of it. If they're happy, it's the end of the term. This is just saying the other side to it, which is also true. If they're not happy, then it's not the end of the term. So that is how we create a contrapositive statement. It remains true, but the whole point is it's a lot easier to prove this at times, depending on whatever statement you're given. Here is how it would be written out mathematically. So if P implies Q, that's our original, then the contrapositive is not Q implies not P. It's a lot easier to prove the contrapositive depending on whichever statement we've been given. So let's give example 7 a go. So let n be an element of all integers. Consider this statement. If n squared is even, then n is even. This is what we started off last with the beginning of the lesson. So let's switch them around and negate them. So if n is even, so that's the opposite of that, is that if n is odd, then n squared is odd. So we've negated both sides and we've switched around the hypothesis and the conclusion. So if n is odd, then n squared is odd. So what we will then do from here is go ahead and prove it. So if n is odd, that means we're going to let n equal to 2a plus 1 to make it odd. Then n squared is odd. So we're going to square it. That's going to give me 4a squared plus 4a plus 1. I can then factorize 2 out. Now, I know we can obviously factorize a lot more than 2 out, but the whole point is that we want our statement to be 2 times something. So I'll show you in a moment. So let k equal 2a squared plus 2a. So what does that give us in total? N squared is equal to 2k plus 1. So the whole point is we just want a 2 here to show that that is initially an even number, but plus 1, which makes it odd. So we've gone ahead to prove that n squared is odd. And if this statement is true, then the original statement must also be true. Let's give it a go again. So there is an error in your notes. This should say n squared plus 4n plus 1. So if n squared plus 4n plus 1 is even, then n is odd. So again, we're going to write down the contrapositive. First, I'm going to grab the conclusion. So if n is, and we're going to negate it. So if n is even, then n squared plus 4n plus 1 is odd. So I've just done the opposite. So let's go ahead. If n is even, we're going to let n equal to 2a, then this second statement must be odd. So let's go ahead and substitute that in. So that'll be 4a squared plus 8a plus 1. Again, I'm going to factorize 2 out. So I end up with 2a squared plus 4a plus 1. And I'm going to let 2a squared plus 4a equal to k. So therefore, I end up with 2k plus 1, which we know is odd. So because n squared plus 4n plus 1 is odd, that means the original statement, or rather the contrapositive statement, is true. Therefore, the original statement is likewise true. All right, that's the end of exercise 6b. I'll see you in the next video for 6c.